Let me explain in graphical method the concept of an amplifier using a transistor in a common emitter configuration. Say I input the signal over here, and what I get out of this box, I don't really know what's inside it. This is a signal that looks like this. Now you can see that it's the same signal, but it has a greater swing or amplitude. Now the phase reversal is something that we'll talk about it later. But you can see that the signal is amplified. Now if you want to know how did the input signal get amplified, then this lesson is meant for you. Now when we look inside the box, we find that we have an NPN transistor. You know that this is an NPN transistor from the direction of the arrow, which points from the positive terminal to the negative terminal, and this NPN transistor is in a common emitter mode. See, this terminal is the emitter, this is the base, and this is the collector. You can see that the emitter is common to the input side and the output side. The input side is between the base and the emitter, and the output side is between the collector and the emitter. The input current will be the base current, which we are going to denote by IB, and the output current will be the collector current, which we are going to denote as IC. See, the direction of the current in the collector terminal will be in this direction. That doesn't matter. It is still called the output current. You can see that from Kirchhoff rules, because the current over here is leaving the circle, so the other two currents have to move into the circle. When the transistor works as an amplifier, the base emitter junction is forward biased and the collector emitter junction is reverse biased. So we will connect a battery and a resistance over here to forward bias this junction, and the battery will be connected so that the positive terminal of the battery is connected to the P side, and will denote this by VBB and the resistance by RB. Now let's take a look at the output side. Here we are going to connect a resistance and a battery. The positive side of the battery will be connected to the negative end over here, and will denote this by RC, and this will be BCC. Now you can see that the voltage over here, if you apply Kirchhoff loop rules in this circuit over here, you can see that VBB is equal to IBRB plus VBE. VBE would be this potential difference between these two terminals. So VBB is equal to IBRB plus VBE. Now let's take a look at the output circuit. Over here we can write the voltage. You have VCE, which is this potential difference between these 2 points. This is C and this is E. So VCE is this potential difference between these 2 points, which is this and this. Again, applying Kirchhoff rule, you can write this as VCC minus ICRC. Just notice that these two expressions are not exactly alike, so that you then don't get confused when you're using these two equations. Okay, now we come to the main part of how this works as an amplifier. See, there is a link between the input and the output circuits. The current in the output circuit, IC, varies with the current in the input circuit, IB. If IB increases, then IC also increases. If IB decreases, then IC also decreases. See? We'll take a look at the output characteristic of a transistor to understand this in a better manner. If you recall, the output characteristic are a plot between the output current IC and the output voltage, which is VCE. hence the name output characteristics. Now, let's just take a look at an output characteristic curve. See, the output characteristics are obtained when we plot a graph between the output voltage VCE and the output current IC, and this is taken for a fixed value of the base current IB. First, the base current is kept fixed, and then by varying the output voltage, the variation of current is plotted. So, we find that the first current increases and then it saturates, and then it stays at the same value even if we increase the voltage, say up to 15 volts. Now, this is an output characteristic, so this is a curve that we get for one particular value of IB. Let's say this is about 20 microamperes because the current is going to be very small. Now say I increase the value of the base current to 30 microamperes. So I get another curve which looks similar, but you get a higher value of the collector current. Say this value of the base current is 30 microampere, and now I get a higher value of the collector current, and you know that the collector current is going to be in milliamperes. Let's say the collector current over here is about 2 milliamperes, and here is close to say 3 milliamperes, which means we are increasing the base current from 20 microamperes to 30 microamperes. The collector current is also increasing from 2 milliamperes to 3 milliampere. If you were to decrease the base current, say from 30 to 20, then the collector current will also decrease. This means that the input current is able to control the output current. So now, for our transistor to work as an amplifier, we need to apply the input signal at the base. The input signal at the base will cause a variation in the base current. This will in turn produce a variation in the collector current, and a variation in the collector current will be reflected by a variation in the output voltage. When this AC input signal is applied at the base, it changes the voltage at the base from VBB plus VI to VBB minus VI, where VI is the amplitude of this voltage. Now we want to obtain an output form which is not distorted. So for there, we need to choose some proper biasing value. In other words, we need to take a proper operating point for our transistor. Sounds confusing? Let's just take a look at it. Once again, we look at the output characteristic curve. I've drawn values for IC for a few more values of the base current. Now this line we're going to draw is called a load line, because the position of the line depends on the load in the circuit, which is the value of the resistance RC. To draw this line, we'll consider 2 points, one where it cuts the x-axis or the VCE axis, and the other where it cuts the y-axis or the IC axis. To find the point where it cuts the x-axis, we'll put IC equal to 0 in this equation, and that gives VCE equals to VCC, and which in our case I have assumed a value of 12 volts. So one is this point over here. Next, to find a point on the y-axis, I'll put VCE equal to 0. Now that gives us IC equals to VCC over RC. Here I have assumed a value of 2 kilo ohm for RC. So this value comes out to be 6 milliamperes. So we have another point over here. Now we will join these 2 points for a straight line, and this line is called the load line. Now, what's so special about this line? See, each point on this load line is an operating point of our transistor, which means if I choose a point over here, then there is a specific value of IB, then IC, which is about 1 milliampere, and VCE, which is little less than 10 volts. So each point over here is called an operating point. Now, say I call this point over here, and if I choose this as the operating point, then at this point VCE is equal to 0, and in this case the transistor is said to be in saturation mode and maximum current flowing through the transistor. So point A is a point at which the transistor is said to be in saturation mode. Suppose now move the operating point to the other extreme end, which is B. At point B, IC is equal to 0, which means the transistor is in cutoff mode. So you can see that there are two extremities. At A, it is in saturation mode, and at B, it is in cutoff mode, and in between the transistor is in active mode. Now we will choose a point which is roughly somewhere close to the midpoint of this line, and this Q point is called the operating point for our transistor. Now, you might be wondering that why do we need an operating point which is somewhere in the middle of the load line? See, when we connect the AC signal, then depending on the positive and negative value of the input signal, the base current is going to vary from, let's say, this value over here to this value over here, because when the input signal is applied, the base current is going to swing with the variation in the base current is from here to here and from here to here. Now, we want to choose an operating point in such a way that the transistor remains in the active region for all values of the input signal. We do not want it to go into saturation or cutoff mode, because in that case the signal will get distorted. So the idea is to choose an operating point somewhere in the middle of the load line, so that variations of the input signal are taken care of and we do not get a distorted signal. Now, once we are made our choice of the operating point Q, we note down the values of IB. Say IB is 30 microamperes, the value of IC, which is 3 milliamperes, and the value of VCE, which is around 5 volts. And then by a proper choice of the input resistance, the output resistance, and the voltages, and this is called biasing of the transistor.